We looked briefly at collets and some other tooling for the mini mill in our last section, and in this section I want to actually demonstrate some simple operations using some of the tooling for those of you who may not be familiar with the capabilities of the mill. But first I wanted to demonstrate the runout of the spindle, and the runout is a measurement of how concentric the spindle is around an imaginary central line. Now all of the tooling in the mill is in the form of an R8 shank that goes up into the spindle, and the tooling mates very precisely with the taper inside the spindle. So we'll measure the runout along the inside surface of that taper. To measure the runout, I've set up a precision measuring instrument called a dial test indicator, and it is attached to the table using a magnetic base and a flexible arm. This indicator measures increments of a 10,000th of an inch. So from 0 to 1 is 1/1000th of an inch, and from 1 to 2 is 1/1000th of an inch, and so forth. The smaller divisions in between the numbered lines are 10,000ths of an inch. Up on this part of the instrument there's a tiny tip, and when that tip is moved, it displaces the needle. I've moved the head down so that the probe of the indicator is now up inside the spindle, and then I'll move the table back until the probe tip touches the spindle. And you can see as I'm moving the table back now, the indicator dial is changing. Okay, with it approximately on 0 now, I'm going to start the spindle. So I'll press the power button. So what we're measuring there is approximately 5/10,000ths of an inch, or a 1/1000th, which is pretty good for a low-cost mill like this. You may remember earlier this number 60 drill from our set of number drills. It is about 40,000th of an inch in diameter. So when you're drilling with tiny little drills like that, obviously if you had run out of, say, 10,000ths, your drill would be going around in circles instead of drilling in a central point. And of course that would be true for larger diameter drill bits as well, but the percentage of error would be much smaller. As another illustration of the precision capabilities of the mini mill, this is a part that I made for a gentleman, and this is made from stainless steel, and his requirement was that it had to be very precise in its dimensions, and it's all metric. So he sent me a blueprint, and he also sent me some high-quality tools that I could use because the tolerances that he needed were better than I could achieve with some of the cheap tooling I had at that time. I agreed to try making a few prototypes for him, and that if he was satisfied, then we would go forward with the project. So this is one of the ones I made from stainless steel. As it turned out, the customer decided not to go forward with manufacturing the product, but it gave me a very good experience learning to read blueprints and work to very close tolerances in some relatively difficult materials such as stainless. This is a 3/4 inch carbide end mill that he sent me for the project. It was brand new at the time, and I believe it was about $160 or somewhere in that ballpark just for this one end mill, but it's very high quality. For one example of work on the mill today, I thought it would be fun to take a piece of 1-inch diameter stainless steel. A lot of times I do my demonstrations on aluminum, but some viewers are skeptical because if they're going to be working with harder and more difficult materials, you know, doing something on aluminum isn't terribly convincing. So I thought today I would mill this flat, and then we'll try drilling 4 little holes to match the 4 holes in this part, and we'll use the digital readout to achieve the spacing according to the blueprint. I cut off a piece of the stainless steel 1-inch diameter stock on the bandsaw, and I've mounted it in a 1-inch collet. This is called a 5C collet. 5C collets are often used to hold materials like this for precise machining, either in a mill or in a lathe. And particularly when you're using a mill, you can mount the collet inside of this gadget called a collet block, which is precisely machined on all its surfaces, and that gives you the ability to rotate the work around by 90-degree increments For example, if you wanted to mill 4 flats on 4 sides. There's a guide pin here, really a little set screw, on one side of the collet block. And when you insert the collet, you have to line up the groove in the collet with the position of that set screw, and then push it back in there. And then there is a retaining ring or locking ring that screws onto the back. Then you tighten that up with a wrench. As the collet is drawn back into the block, the taper squeezes down very tightly and holds the workpiece in place. I've mounted a milling vise on the table. Before I begin any machining operations, I'm using the dial test indicator along the fixed jaw of the vise. And as you can see, there's very little movement, indicating that it's parallel with the table movement. For our first operation, I'll use that 3/4 inch end mill to make a flat face on the top of the workpiece. So I have the collet block assembly now mounted vertically in the vise so that I can access this area to mill it flat. Now I want to establish a 0 depth reference point for the end mill, so I'll use the 3-spoke hand wheel to lower the tool gently until it makes contact with the top surface of the workpiece. And of course that's not flat. I won't be using the X and Y coordinates until later on, but I'll go ahead and set all of them to 0 for now. Now I'll move the table to the left to give me some clearance to begin cutting. Once I clear that right side of the workpiece, I'll engage the fine feed control for the Z-axis. And now I'll lower the Z-axis down to a depth of 1/2 millimeter. I've set the RPM to about 1,000. I'm not sure what the optimum speed would be for this combination of material and cutter, because it's been a long time since I've worked with either one. So we'll start with that and see how it goes, and just feed slowly by hand, make sure everything's going all right. When I made the first pass, I didn't have the end mill quite far enough back, so I missed a little section there. But what I'm going to do is drop it down just by about 1/10 of a millimeter to make a finishing pass, and I'll clean up that back edge on the next run. I'm also going to run at slightly higher RPM this time. So I've got it at about 1600 RPM. You can see a little bit of roughness in that cut. As I mentioned, it's been quite a while since I last used this end mill, and I remember now that I did a job a few years ago where I was cutting some material and somehow chipped the face of one of these flutes. So I think that's what's causing the roughness. But I'll make one more light pass and see if we can clean it up, and I'll run it even higher RPM and see what happens. Yeah, I'm up about 1900 RPM this time. I'm going to drop it down another 1/10 of a millimeter. All right, well that looks a lot better, and later on I'll demonstrate some other cutting tools, and maybe we can get a better quality surface on that with one of the other tools. But let's go ahead now and set up to drill our 4 holes. For the next operation, I need to change from the collet that was holding the 3/4 inch end mill to the drill chuck, and so I had to use the spinner tool that I made for the drawbar. And since I'm using it routinely now, I temporarily glued this 17 millimeter socket onto the end with some quick grip glue from Walmart, which I use for all sorts of temporary holding requirements. I like quick grip because it sets up very rapidly within a minute or two, and it can be easily and completely removed with some denatured alcohol when the job is done. In order to use the digital readouts to locate the holes according to the plan, I need to use an edge finder. And there are several types of edge finders available, but I generally use this type, which is called a wiggler. I find it is convenient and less troublesome than some of the other types. A potential disadvantage of a wiggler is that it's relatively long, and in this case, with the head of the mill all the way up and the wiggler mounted in the drill chuck, I don't have enough room to get to the edge of the workpiece. So that's not too serious because I can just use a 3/8 inch collet to hold the wiggler and then change over to the chuck. Other types of edge finders generally are shorter than this, so they would work better in this particular situation. This hole in the side of the spindle is where the pin engages to lock the spindle in place. I didn't notice this until I'd been working with the mill for a while, but there's actually two of these holes, one on each side. An advantage of having two holes is that you never have to rotate the spindle more than half a turn before it locks up with the pin. But a disadvantage is that you don't know which side this groove has to be lined up with to mate with the internal pin. So I've made a mark with a Sharpie pen here to show which of the two holes the pin is aligned with. I'll experiment with that and see if that helps me to get the proper orientation the first time. We need to position these four holes equally distant from the center, and the easiest way to do that is to use the edge finder to find the center of the workpiece, and then we can use the digital readout to measure 1/2 the distance, which in this case is half of 11.2 in the X and the Y direction, to find the center for each hole. So to find the center of the workpiece using the edge finder, we first want to find this edge, then the opposite edge in the X-axis, and then repeat that in the Y-axis. The DRO has a function to take 1/2 of the distance between 2 points, so that will help us find the center point quickly. Now with the wiggler tip out of the way, I'll move the table to the right so that we can reach the left side of the workpiece with the wiggler tip. And once we have enough clearance there, we'll start the spindle again and repeat that same process on the left-hand side. So you can see it first appears to stop moving, and then as we continue, it will suddenly pop out. And there it is. At this point, you can see that the DRO reads 27.54 millimeters. If we zoom in on the X-axis on the DRO control, you can see that there's a 1/2 function, so I'll now press that button, and that gives me 13.77. So now I move the X-axis 13.77 millimeters to the left, and really all I have to do is watch the DRO as it counts down to 0. And when it gets to 0, then I'm at the center of the workpiece in the X direction. Overshot just a little bit, but that's close enough. 0.01 millimeters is well under 1/1000th of an inch. Now we have to repeat that process for the Y-axis. I've now centered the wiggler on the Y-axis as well as the X-axis. It's essentially exactly on center in both axes. This will be our reference point for moving to each of the 4 hole positions. We see that the threaded holes are for M2.5 or 2.5 millimeter screw. So I think we'll drill our holes in our plate to 3 millimeters to provide clearance. These are M2.5 by 10 millimeter screws, Phillips head. You can see they're really pretty tiny. And the tap wrench, of course, is tiny too. And tapping in a relatively tough material like stainless steel with a very small tap like this can be an interesting exercise, we'll say. Cutting fluid is very important to keep the tap from seizing up in the hole. And of course you have to continually back it off, and in some cases totally back the tap out to clear the chips so that you don't get the tap seized up in the hole and break it off. Let's go ahead and get set up and drill these 4 holes. And I'm going to start with a number 1 center drill. So I'm at the center of the workpiece, so let's offset by 5.60 in each axis. I've offset now 5.6 millimeters in both the X and the Y axis. I'm going to make the upper right hole number 1, and then below that will be number 2, and then 3 and 4 on the other side. So you can see the X and the Y axes on the DRO are at 5.600, and the Z axis reading is just arbitrary because I did not zero that. Let's go ahead and get started with hole number 1. I'm going to put a drop of Tap Magic cutting fluid there just to help with the stainless steel. Since this is a small drill bit, I'll run the RPM up to about 1500. Our depth is about 2.5 millimeters now. I'll leave it at that. At this point, we have a choice. We could remove the center drill and go ahead and put our 3 millimeter drill in place and drill this hole and then put the center drill back in and so forth. But it's actually quicker when you have a DRO in most cases, and especially if you're only moving a small distance between holes. You can take the center drill around and drill all 4 of the starter holes, then replace the center drill with the drill bit and go and drill all 4 of your regular holes. So I'm going to do it that way because it's actually quicker. So we'll put a little drop over here, and then we'll, watching the DRO, we'll go through the 0 point. Okay, let's drill our second center drill hole. And I'll drill it 2.5 millimeters deep just for consistency. And now I can even leave the mill running. I'll just move over to the next hole. Alright, so I've finished with the 4 center holes, and now since I'm in this location I can go ahead and start here. Since we're already in position for that, we'll start there and work our way around. I decided that a 3 millimeter drill was a little bit larger than necessary, and so instead I'm going to use a 2.6. Although the screws are nominally 2.5 millimeters, their actual outer diameter is about 2.42. So 2.6 will give us a tighter fit and make it a little bit more challenging. I'm going to drill these to a depth of about 1 millimeter. Later on we'll cut this into a disc about a 0.5 millimeter thick, but I want to make sure I go all the way through. So I'm going to put some Tap Magic in each of these holes. And now we'll go ahead and drill. I'm going to use the same RPM, about 2000 RPM. I'm going to use a technique called peck drilling, where I run the drill in and back it out so the chips can clear, because relative to the diameter of this drill bit, a 1 centimeter hole is actually considered a deep hole because it's more than 3 times the diameter of the drill bit. So peck drilling is the way to go. And I'm going to add some more cutting fluid. I decided to only go 8 millimeters deep. Now I'll do the next 3 holes in succession. I should have done this earlier, but let's drop one of our screws in for a test fit. Looks good. The next thing I want to do, and I probably should have done it before I drilled the holes, but it doesn't really matter, As I mentioned earlier, I'd like to do a cleanup pass on this top surface, just a very light finishing cut to remove some of the markings that were left by that end mill. So let's get set up for that. The tool I'm about to use is this indexable end mill, and indexable means that it uses inserts as the actual cutting faces of the tool. And of course these inserts are removable and they can be rotated. They're triangular, so you can get 3 different cutting points on them. So as one wears, or if you happen to get it chipped, you can rotate it around to the next one. When all 3 points have been worn down, then you replace them with new inserts. So it's a very good system, and the quality of finish you get on these is really pretty amazing, especially considering it's a low-cost mill intended for home shop use. This indexable mill has a cutting width or cutting diameter of 1 1/4 inches, which is good because it's just a little bit bigger than our Workpiece, which is about 1 inch. Now I'm going to use the Z-axis 3-spoke hand wheel to gently lower the head until the tip of the tool touches the top surface of the Workpiece. And then I'll set the Z-axis to 0. And that gives me a way to measure my depth of cut. But more importantly, it ensures that I don't start out by taking a depth that's too great and either chipping a insert or causing problems on the Workpiece itself. Now we can offset the tool past the edge of the Workpiece. I want the center of the cutting tool to be aligned with the center of the Workpiece, and since I have my previous DRO readings, I'll just move the table until the Y-axis reads 0. That will align the center of the spindle with the center of the Workpiece. And because the cutter diameter is slightly larger than the Workpiece diameter, I should get a clean cut all the way across. I'm not real sure what a good spindle speed is for this operation. It's a relatively large diameter cutter, so you have to keep that in mind and not use too high a cutting speed. But on the other hand, carbide tools generally are run at higher speeds. So I'm going to run at about 1,000 RPM. And those of you who have more experience can comment as to whether that's too high, too low, or maybe just right. So let's go ahead and give it a try. So I'm going to lower the head down just a little bit. I want to take a very shallow cut. And then I want to make sure that the Z-axis is locked. I've engaged the Z-axis fine feed control. So I'm now going to lower the tool down 0.2 of a millimeter below the top surface. So it'll be 0.2 millimeters. And of course I want to make sure that the head is locked to the column so that the head doesn't drift down due to vibration. And I'm feeding by hand. I think you can see that that did a real nice job, and I'm satisfied with that finish. I forgot to mention that before that cutting operation, I locked the Y-axis to avoid any undesired or unwanted movement in the Y-axis while I'm cutting along the X-axis. So in general, anytime you're cutting in a particular axis, you want the other 2 axes to be locked. The last operation I want to do for this section of the video is to lightly chamfer these 4 holes. And to do that, I'm going to use the same number 1 center drill that we used to make the starter holes, but this time I'll go just a little bit deeper. Well, that wraps up this segment of the video. In the next series, I'll cut a disc off of here, and we'll also look at a way to finish this outside diameter of the Workpiece. Right now that has a very sharp edge on it that I would like to remove, but we'll save that for next time.